Thank you very much, and thank you very much for the invitation. Okay, I'm going to talk about thickness and a gap lemma in RD. Well, thickness was at the beginning defined in the real line. That's a notion of size of a set. And the gap lemma is a result that under certain conditions, depending on the thickness, can ensure that two compact sets intersect. I'm going to start with the definition of thickness in the real line, but first we have to see a useful way to look at a compact set in the real line. Let's say that C is a compact set in the real line. We can consider I1, that is the convex hull here. Can you see the arrow? Yes, great. So the convex hull is the first interval, and then we can consider the sequence of gaps that are the path-connected components of the complement. They are open, and there are finite or countable many of them. And we can take that sequence in a way that the diameters are decreasing, right? And then we define, every time we erase a gap, we define L and R, the left and right pieces that are next to the gap. And in this way, we can define a notion of size of the set depending on the proportion of these lengths. To be more specific, the same picture is here. Newhouse defined the thickness of the compact set as the infimum over all the quotients of the length L over the length of the gap that is next to it, and the length of R over the length of the gap that is next to it. And intuitively, this notion of thickness, when this notion of thickness is large, it means that all these quotients are large, and so all the proportions are large. It means that the set is large everywhere and at every scale. There is another very common notion of size that is the Hausdorff dimension, and there is a relationship between them. The Hausdorff dimension of a set is larger than this number depending on the thickness of the set. You can find this, the proof of this in the book by Palix and Takens. This says that if the thickness is very, very large, well, this is going to be very close to 1. And so the set C is almost full dimensional, right? But on the other hand, there are sets of positive Lebesgue measure, and so full Hausdorff dimension with thickness 0. To see that, you can consider an interval and then union, an isolated point, and this quotient is going to be 0 because the length of the point is 0. But sorry. Is that better? Yes, sorry. And well, I was just saying that there are sets of positive Lebesgue measure with thickness 0. You can consider an interval union an isolated point. That's an easy way to see that. But there are sets without isolated points that also satisfy that. Well, let's see our first example, maybe the most basic one. That is the middle epsilon Cantor set, which is obtained by starting with the interval 0, 1, and then removing inductively the middle epsilon, the middle interval with relative length epsilon. So here these lengths are 1 minus epsilon over 2, and we can continue this process inductively. So in the step M, the intervals have length lambda to the m, and the new gaps have lambda to the lambda to the m-1 times epsilon, right? So the thickness that was defined in this way is the infimum over all these quotients, which is exactly 1 minus epsilon over 2 epsilon. This is of the order 1 over epsilon. This is going to appear at the end of the talk. Well, with this notion of size, Newhouse was able to obtain his maybe famous Gap Lemma. He was motivated by problems in dynamical systems to see when to Cantor sect intercept. He proved more specifically that if you have two compact sets in the real line such that neither of them is inside the gap, a gap of the other one, and the product of their thicknesses is larger than 1, then the intersection is non-empty. And this proof uses a lot the order structure of the real line. So generalizing this to RD is a priori not trivial at all. There were some attempts or some definitions of thickness in a more general context. Sébastien Biebler defined a notion of thickness for dynamically defined sets with IFSs in the complex plane. I'm going to compare his definition with mine later during the talk. And Feng and Wu define another notion of thickness that is useful to study some sets. They were trying to see how many times you have to add E plus E plus E plus E in order to see that the interior of that set is not empty, depending on the thickness. And well, with Kenneth Falconer, a year ago, we gave a different notion of thickness in RD, that is this definition here, in which we consider a compact set in RD, and we define E, the external component. And after that, well, we have this, let's say these two green potatoes in this case, and we start erasing holes inside. We can erase the holes in order of decreasing diameter too. And then, oops, sorry. And then looking at these distances between the new gap with the previous one and the external component gives a notion of how thick is that, well, that part of the green set that is still alive compared to the diameter of the gap we are removing. So this is a definition of thickness. And there are pros and there is a drawback. The pros is that this is in a number in zero infinity. It is invariant under similarities. And in the real line is equal to Newhouse's thickness. And we also got the first Gap Lemma in RD. But there was a big problem that the sets that are useful, the sets that have positive thickness, are like those sets, removing maybe a lot more holes, but they look like that, like cutout sets. But in the case that we have the most classic examples, like totally disconnected sets, like product of Cantor sets, for example. In this case, the external component is everything except the set, right? And there are no gaps. So this is bad for our definition, and our thickness was going to be 0 in this case. And I want to also say that these kind of sets are like famous and important, not just in geometric measure theory, also in dynamical systems. Okay, now I'm going to give you the definition of thickness that is new. But for that, I'm going to give you the context. We are going to work, of course, in RD. I'm going to consider here the distance that is associated with the infinity norm, but we can take any other distance associated to the norm. But I prefer this one because of the way the cubes are packed in RD. It's kind of convenient. And all my cubes will be closed. If I say ball by mistakes, I mean a ball in this distance. So I mean cubes. And we are going to write any compact set in this way as an intersection of unions of cubes. This is a Moran construction type. And N means the level of construction. And for each word of length N, we have a set in the level N. Each cube Si contains many children, Sij, and there are no assumptions made on the separation of the cubes or anything. They can be overlapped, whatever you want. And for any infinite word, this means that we are considering sets that are nested. The limit of the radii are going to 0. In this case, we say that this family Si is a system of cubes for the compact set C. In the case of the classical product of the same Cantor set, well, it's quite obvious the family of cubes we are going to consider. This is the cube, the first cube that is associated to the empty word, and then we have 4 cubes that are at the first level. Oops, sorry. And then we have children there, and so on. So as I told you, here there are no gaps, but we need to define some kind of notion of gap size. We may not have gaps, but we have a notion of room that we can define here. There is some room that is not filled by the set, and I'm going to use that. I'm not going to define gap because there are no gaps. So I defined for a given cube, well, I'm going to use this picture. For a given cube Si, I define the notion of gap size associated to this cube as the maximum distance over all the points X here in the cube to the compact set C. So for example, well, my picture is a bit horrible, but I believe the point that is maybe far away, really far away of everything is this one here. And H would be the radius of this ball. I'm sorry, here my picture is a bit wrong because there is a ball that is like in norm 2, but it should be a square, right? I forgot that, and well, I'm sorry about that. It should be a square. With this definition of gap size, if we have any point in the cube Si and any radius that is larger or equal than this number, the closed cube with center Z and radius R intersects the compact set C. And if we consider any other number that is smaller, any other radius that is smaller than this number, well, there is a ball with some center inside the cube that doesn't intersect the set. So with this, we are able to give a definition of thickness in RD. Well, now it's easy. We have to consider the infimum over the sizes of the children, divided the size of the gap or gap size or the room we have there. And well, I told you that I was going to present the Gap Lemma, but in the case of RD, in the higher dimensional case, I'm going to need another assumption. So I'm going to give this definition too. We say that a system of cubes is R uniformly dense if for every cube in the family and for every cube B that is inside the cube of the family, with radius that is not so small compared with the radius of SI, there is a child contained in the body. I don't know if you can see that. For every cube in the family, let's say that R is, I don't know, 1/4 here, for example. So for every cube of relative radius, like a quarter of the other one. Sorry, it's smaller. We need to ensure that here somewhere there is a child. I can consider another cube, for example, here, and I also need to have a child there, and so on, right? That's why I called it dense in some sense. Do you have any questions? Okay, so with this definition, I was able to prove a Gap Lemma in RD. If let's assume that we have C1 and C2, two compact sets in RD with respective systems of cubes, S1I and SL2, for which there is an R between 0 and 1/2, satisfying that the product of their thicknesses is larger than this number, depending on R. And both systems are uniformly dense. We also have to assume these conditions that are quite mild. The first one is that the first compact set intersect a shrunk version of the set we start with the other one. And well, the size of the set we start with cannot be too small one respect to the other one. Under all these conditions, we can ensure that the compact set intersect. In the real line, our notion of thickness is equal to Newhouse's thickness for the most natural system of cubes. Thickness is a number in 0 infinity. The definition is invariant under homothetic functions, which is equal to the case of the real line. But unlike Newhouse's Gap Lemma, we need to, at least for my proof, we need to ask for this condition here. I believe, I'm not sure if we can remove this condition, but I believe we cannot do that intuitively. I have an intuitive argument to explain that. I'm not sure if I have time, so I'm going to continue. And in case you want to know about that, you can ask me. So as I already told you that the conditions in the third item are quite mild, and they can be seen as a stronger version of the hypothesis that each Cantor set is not contained in the gap of the other one in the original Gap Lemma. And all these hypotheses are robust under perturbations of the Cantor sets. And this is maybe more important for people in dynamical systems. Well, it seems reasonable in all the other hypotheses, but maybe you can be suspicious about this one if this is stable under perturbations. And I'm going to explain why that's stable. If we consider a function from Rd to Rd that is invertible C1 and for which the matrix derivative is very, very close to the identity, and we consider a compact set and certain system of cubes, and we want to apply f to all of that. So when we apply f, we have f of c, and we can consider also f of the cubes, but now they are not cubes anymore, right? A priori. So what we have to consider is this other system of cubes that I call Ri, that are cubes that are as small as possible, containing f of Si. And considering that system of cubes, I was able to prove that the thickness of f of c doesn't drop so much because it's controlled below, but the thickness of c divided this other expression that is very small when epsilon is very close to 0. Well, now I'd like to give the first example, or in fact, a family of examples for which we can apply the Gap Lemma, and we can get the thickness and everything explicitly. So we are going to be in Rd, but my picture is in R2. We consider n a natural number, larger or equal than 2, and L, which is the length of this side of the cube of the first level, and we are going to consider a corner Cantor set with that side length and n cubes in each direction, right? So if we consider that, this green distance here has to be, because we are in -1, 1 square, has to be 2 minus NL over n minus 1. And one can get the thickness, and that's L over G, which is this quotient here. And it's easy to see that this set is R uniformly dense for this value of R. And the reason for that is that when we consider a square with length side 2L plus G, which is this length here, you can be sure that you are going to have a child there. Because, well, if I start with a cube here, I have 4 children. But if you move it, you are like erasing a part of certain cube, but you are getting a new part of the cube on the other side. And even if you move, there is always a cube that is going to be contained in this in a cube with this radius. I fix n, that is the number of cubes that are going to appear in the first step in every direction. For example, n equal to 4 in that case. So, and so I want to put 4 cubes here, and I have to choose some side length. So L is the side length of the first level, right? So, for example, if this is L, well, it depends how many cubes I put here. If I put 4 of them, then for L must be smaller than this length, that is 2. And the remaining space that is here is 2 minus 4L divided by 3. That's the sheet that appears there. Okay. Any other question? Which M? I've been told that my M seems to be an M. So if this purple N looks like an M, it's N. Okay, sorry. Okay, so in this case, we got the thickness, exactly the number that is the thickness, and the R that we need to get the uniformly dense condition. So we can apply the Gap Lemma, but of course, we are not going to apply the Gap Lemma to 2 sets that are exactly like this, because the point here in the corner is going to be forever in the set in every step of the construction. But we can apply any homothetic function to each of them in such a way they are not far away from each other, and use the Gap Lemma there, for example. And we can also use, for example, the robustness that we saw before and get another stuff for it, just to say something. Well, now I'm going to compare with Vebler's definition in the plane. Vebler's definition of thickness, well, was just defined for dynamically defined sets, so for IFACs in the complex plane, and it's quite involved. It's kind of difficult to get. There are many definitions in between in order to get the thickness at the end. And in the previous example, for example, the thickness given by Vebler is equal to this number. So if you compare my thickness, that is this one here, with his thickness, that is this one, we have this inequality, at least for this family of sets. And okay, this is for every n. And when n is large enough, this is a very big constant. So my thickness is way bigger, at least for many examples. And that's very good, because when we are trying to prove that something is useful to apply the Gap Lemma, we have a condition that is the product of 2 thicknesses being larger than something. With Vebler thickness, this is small. With my thickness, it's bigger. So it's better. This is better. Well, he also requires a much smaller uniform denseness. That's maybe a problem, because it means that if you are in certain cube, and you take a very, very small cube compared to this size, you necessarily need to have a child there. So this is a worse condition, because, well, you need to have children like everywhere. This is super dense. So my hypotheses are better. And I also allow the sets we start with to be different. So for example, I can have a compact set starting with the construction in this cube, and another one starting here, and everything is fine. And well, also my definition is simpler. My proof is also simpler, different, and more flexible because it's an inductive proof that allows to change the role of the sets while doing the induction, right? This is more like the proof, Newhouse's proof in the real line. He also has certain change in the roles. So this is somehow more reasonable. Well, I was also able to get a lower bound for the Hausdorff dimension, given a compact set with thickness tau, where each cube has at least M0 children, and we assume a strong separation condition. The distance between two siblings is larger than a constant times the radius of the father. Then we have this lower bound for the Hausdorff dimension of the set, depending on the thickness, and depending also on this M0. That is the number of children we can ensure. Just as a comment, we saw before an analogous bound for the case d equal to 1. In this case, my proof cannot use the order because there is no order in RD. But my bound in that case is a bit worse, but it's not so different from the bound we got before. Well, this is an easy corollary that is an application to distance sets. If we fix a direction B in the sphere, in the unit sphere, we say that T is a distance between points in the set if the difference of the points in the set is T times V. And we can consider the sets the set of all distances in direction B. If we apply the Gap lemma to the sets E and E plus TP, we get that for, and there exists an R in 0, 1/3, satisfying that the thickness is larger than this number, and we also have the R uniformly denseness. Using the Gap lemma, we can ensure that for any direction B, we have this interval contained in the sets of distances with direction B. And here I want to comment that we know that if a set has large thickness, then it has large Hausdorff dimension. And by a result by Matila and I don't know the pronunciation, I'm writing it for that reason, Scholling, I don't know, for a result made by Matila and Scholling, we know that the distance set contains an interval. But this is stronger because it implies that in every direction we have the same interval independently on the direction. Of course, the hypotheses are stronger too, right? Well, now I'm going to change a bit the topic. It's not so much. But I started studying the Gap lemma and the thickness and all of this because I was interested to know when the intersection of Cantor sets or compact sets was non-empty. And the reason for that was the fact that I was studying patterns or homothetic copies of finite sets inside a compact set that is large enough in some sense. So I'm going to talk a bit about that, and I'm going to connect everything in a few slides. This is an interesting result. Broderick, Fishman, and Simmons proved that for epsilon sufficiently small, the middle epsilon Cantor set contains an arithmetic progression of length 1 over epsilon divided by the logarithm of 1 over epsilon. Their proof is based in some tool that is, well, it was very new to me at that point, that is the potential game. And as a general idea, there are certain rules and two players, a player that is called Bob, who decides where we are going to zoom in. Well, I'm going to do it in the real line, but it's the same in general. Let's say that we have, I don't know, the middle third Cantor set, and Bob decides where we are going to zoom in, and then Alice decides what we are going to erase there. So for example, if Bob starts with this ball, Alice can, let's say that erase an interval of proportion, a third of what Bob played. So she can erase, for example, this one. And we are interested in winning sets that are subsets of the board game. So subset here. And we say that a set W is winning if Alice has a strategy guaranteeing that whatever Bob plays, Bob is going to continue like zooming in, and Alice is going to continue erasing inside the place Bob zoomed in. And she can ensure that she erases the complement of the set there. So the limit point for Bob's moves belongs to the set W. In some sense, being a winning set for certain parameters can be considered as an notion of large size for the set. For example, I'm going to give you an example because I believe this can be new for you. Let's say that I want to show that the middle Cantor set is winning, and Alice is able to erase something of proportion 1/3. When Bob plays the first ball, she erases this interval. In the next step, Bob can choose another ball of proportion 1/3. In any case, well, if Bob plays here, the game finishes and everything is fine. For Bob, it's convenient playing here or here to get the most of the set, the biggest set possible. Let's say that Bob plays here, the ball here, then Alice can erase a third of the proportion, and so on. So at the end, we can ensure that Alice has a strategy that is erasing the middle interval in the place Bob is playing his interval. And in that way, this set is winning because the limit point is going to be here. Yes.
What is like a ball that only has a tiny end piece of that?
That's better for Alice. In that case, Bob is not so clever. I'm going to show you why. Let's say that because we cannot decide what is doing Bob, but we have to choose what is convenient for Alice, right? So let's say that Bob decides that he's taking this interval. Alice already erased this part. She has to erase just what is here, and it's not in the Cantor set. She can erase this part too. Well, just that. That is even smaller. And we can continue the process here. But we are always erasing what is.
But if there is only like 10% of the set on the right left, and she She would have to erase something at the end. If he chooses something.
He can choose to erase something smaller if she wants, or pass her turn.
So she doesn't have a fixed ratio she has to erase.
She has an upper bound for what she can erase.
Oh.
She wants to erase as much as possible.
Okay.
But there are rules. She cannot erase everything because otherwise.
Yeah.
Right. Okay. So, okay. As I told you before, I was interested in these copies of finite set. And the presence of a homothetic copy of a finite set is related with an intersection being non-empty. The set C contains a homothetic copy of this set if and only if there is a lambda for which this intersection is non-empty. If an x is here, it means that x plus lambda pi is contained in the set for every I, right? And I was interested in the potential game I mentioned before, because the winning sets for the potential game have very good properties. If this set C is winning with certain parameters, this translation is also winning. The intersections are also winning with other parameters, but we know how they behave. And finally, there is a lower bound for the Hausdorff dimension of a winning set. So if I can control below the Hausdorff dimension of this set by something that is a positive number, I know that this intersection is not empty. In fact, I know that I have a lot of copies of the set P inside C. Well, by establishing a new connection between winning sets and thickness in the real line, I proved a couple of years ago that for any compact set and every finite set P with at most this number of elements, the compact set contains many homothetic copies of P. Afterwards, with Kenneth Falconer, we proved an analogous result for our definition of thickness. I'm going to tell you what was the definition of thickness. It was the one with the green potatoes and the holes inside. And in that case, we got that we were able to guarantee copies of any finite point configuration with this number of elements, depending on the thickness of the set. And to prove that, we established also the connection between winning sets and our definition of thickness, and proved a lower bound for the Hausdorff dimension of the intersection of countably many sets, depending on their thicknesses. And now, with my new Gap Lemma and the new definition of thickness in RD, that is useful also for disconnected sets, by changing the rules of the game, I have to change the game. I'm erasing, Alice is erasing neighborhoods of spheres now instead of just balls. And with that, I was able to establish a connection between winning sets with that game and the new notion of thickness. I got a lower bound for the Hausdorff dimension of the intersection of countably many sets depending on their thicknesses, and also prove an analogous result guaranteeing homothetic copies of finite sets with at most this number of elements. And as a comment, I didn't forget the D there. The result is like that. And the reason for that is quite intuitive, is related with the fact that in the previous game, we were erasing neighborhoods of points, and a point is a zero-dimensional set. And now we are erasing neighborhoods of spheres. Well, in the case of the infinity norm, it's something like this. but it's a D minus 1 dimensional set. So somehow the exponent is tau to the D minus the thing that is here. So in one case is D, and in the other one we get 1. It's related with the change of the game, and the fact that I'm erasing neighborhoods of spheres is intuitively related with the fact that I'm dealing with disconnected sets. If we have something like this, basically what I'm trying to erase is considering the room we have here inside. I consider the union of this, right? To erase the gap with the game. And when we continue in another level, well, Alice erases also a neighborhood of smaller, at a smaller scale, also neighborhoods of these spheres in the respective node. Well, that's all. Thank you very much for your attention.